Dear student, Assalamu alaikum. Hope so you are fine. In the previous lecture, we have discussed about the magnetic field and the problems related with it. Now, in the today's topic, we will discuss about the Hall effect and the problems related with it. How you are going to implement the Hall effect formula to solve the numerical. Now, how you define the Hall effect? Up till now, we have just look at the effect of the magnetic field, the external magnetic field on a single charge particle Q, and we have seen there will be some deflecting force which was FB is equal to QV cross B. But now, if you will have a current carrying conductor, if you will say it's a conductor, so large number of the electrons will be moving there. So now you will have a current which is basically the charge flowing per unit time. So if you will have now a conductor that has some current I and you will place it in the magnetic field, so what will be the change there? You will see that some charge carriers build up on one side of the conductor and some of obviously leaving the deficiency there and creating a potential difference V across the strip. So the polarities of the side indicates the sign of the charge carrier. Basically, this is the Hall effect. Now we are going to discuss it in detail. You can see here a figure A. This is basically a piece of a conductor which is placed in the magnetic field B. Now, this cross sign shows you the magnetic field is into the board. In other words, if I is in negative y direction, you can see here it's pointing down. Magnetic force you will find where it will exert, but the B field, which is a uniform magnetic field B, it's in the negative z direction. So since you have the formula FB is equal to QV cross B, so obviously the direction where the current is flowing, if you will have electrons, it will move in the opposite direction. If it will be the protons, it will move in the same direction. So in the first figure, we are just taking the electrons which are moving, so they are moving in the up direction. So here, by using the formula QV cross B, the V will be in positive J, B is minus K. So you can just multiply J cross minus K. Do it in your copies now. You will check by the rule. I have told you, make a circle and write it there I, J and K in anti-clockwise direction and get the answer. So you will check it at your home that FB will be pointing in the positive I direction, positive X direction. So what does this means? This means all the electrons here, all the charged particle here, they will be deflected towards this direction wherever the magnetic force will be acting. So they are not moving in straight line. The magnetic force which is present here and the current is passing through it, it will deviate it from the straight path, and all of them they will bend. This black line will show you the bending. So all of the electrons they are moving towards this side, which will be right side of me. This is positive x direction, and leaving the deficiencies on the opposite side. So if the electrons are moving, so leaving the positive charges on the left side. This is the figure B where you are seeing the equilibrium condition. Equilibrium condition means the forces are balancing each other, and you will see the electric force and the magnetic force they are balancing each other here because the current is flowing. So obviously you will have the electric force there will be the electric field here, which will be basically due to the presence of these static charges plus and minus. This is the equilibrium condition from where this electric field will be there, will be coming. This is basically due to the charge imbalance because due to the magnetic force FB, electrons are moving towards right, creating the deficiency on the left side. So this is positive, this is negative. Now they are not movable charges, they are static charges. So wherever the charge is, there will be the field, and the field lines are pointing from the positive for the positive charges radially out. So you can see the direction of E, which is shown by the blue arrow here. It's pointing towards the from the higher potential towards the lower potential. So when the equilibrium will reach, the two forces, one of them will be QE, that is the electric force, and one of them will be QV cross B, which is here QVB, because all the are perpendicular to each other. V and B are perpendicular to each other, so they are balancing. So here only one electron is shown just for the simplicity. So these types of large number of electrons are there in this piece of conducting strip we have taken. So you will see all the electrons when the equilibrium will obtained, all the electrons will pile up on the right side, all the deficiencies will be on the left side, and this charge imbalance will create a potential that named as Hall potential. So you can see here from this figure, a strip of a copper carrying current I is immersed in the magnetic field B, and the situation is immediately after the magnetic field is turned on. So the curved path that will be taken by the electron is shown here. So the situation at the equilibrium which quickly follows is shown in the figure B. And now you can see the left side is at the higher potential for the figure C, while for the figure C, you can see the left side will be at the lower, and for the figure B, it's at the higher. So this is for the proton, this is for the electron. So this left side is at the higher potential, this is at the lower potential, and this is basically the inbuilt potential. We are saying that is called the Hall voltage. While for the figure C, this is reverse. The left side is at the lower, and the right side is at the higher potential, and the field direction is also reverses because the protons are moving here, and the force direction is again same, but due to the presence of the same amount of the current which is flowing in the same direction, if you will reverse the current direction, then obviously this direction will changes. So I have explained the equilibrium that it quickly develops in which the electric force on the electron has increased enough to match the magnetic force, and when this happens, you have seen in the figure B that the two forces due to the B and the E, they are balancing, and the drifting electrons then move along the strip towards the top of the page at velocity Vd with no further collection of the electrons on the right edge of the strip, and therefore no increase in the field E. So since I have explained that when the equilibrium is reached, and there will be some Hall potential that will be associated with the electric field across the strip with D. So you can have this relation V equal to ED. Remember this relation from the electrostatic, that you will have the uniform field E, then the potential difference V is ED. So here, when the equilibrium will obtain, electric force is equal to the magnetic force. E and E, the charge will cancel out, and you will have simply E equal to VB. V is basically the velocity, that is called the drift velocity of electron. And also you remember this formula discussed in the chapter 26. The drift speed is related with current density divided by the number density in the electronic charge. So current density is related with current over area and NE. So just using 1, 2, and 3 equation, you can just simplify it and find the Hall voltage V, which is capital V here. Although you can just put the subscript H here or not, it's the same thing. So this V is now the Hall voltage because it's the inbuilt potential there. D is the thickness, I is the current, V is the external magnetic field, N is the number density, small e is the elementary charge, and A will be the area. Now, more simplified form, the area can be written as LD, where L is the length and D is the thickness. So in terms of length, you can just replace it as N is equal to IB divided by EVI. So the number density can also be calculated by using this Hall effect. So I hope so this Hall effect is clear to you. Now we are going to implement it to the problems. So this is the example one. From your book, you have seen here a cube which is basically placed here at the origin, and what you have to do, the figure shows a solid metal cube. Since it's a metal, obviously the electrons are moving, so don't need to tell us which particle will move. So for the metal, definitely it's the electron of the edge length d, which is 1.5 centimeter, moving in a positive y direction at the constant velocity 4 meters per second. So basically velocity and b will tell you where the deflecting force will act. So the cube moves to the uniform B field of the magnitude 0.05 Tesla in the positive z direction. Which cube face is at the lower and which will be at the higher means you have to just explain the Hall potential here, where will be the direction of lower and higher potential. So first of all, V cross B, just do it in your copies. V will be pointing in positive J and V is pointing in positive K. So J cross K will give you what? It will be I or negative I. Just check it here. J cross K, because this is in positive J, and this is positive K. So V cross B, you will just check there. It will be I, J, and K. When you will make a cycle, so it will be positive I. But since the electron is moving, so you will also count the charge sign. So due to the charge sign, you will see here the direction of the magnetic force is in a negative I direction. So this is the thing. And when the equilibrium is obtained, all the electrons they pile up on the left and leaving the deficiency on the right. So that shows the left side will be on the at the lower potential and the right side will be at the higher potential. This is all the thing which is explained here. And for the second part, you have to calculate just the hall voltage. So all the data is given, V given, B given, and the thickness D or the edge length D is also given. So just put the values here, and this is your task. I will discuss it in the online session, class session. From you, have you read this slide or not? And just you will tell me how this 3 millivolt can be obtained for this case. So this is the problem 13 of your book, Halidor, Resnick and Walker. A strip of the copper 150 micrometer thick and 4.5 millimeter wide is placed in the uniform B field of the magnitude 0.65 Tesla. Current is given 23. You have to calculate the hall voltage, and the number density of the copper is also given. Simply use the formula which we have derived a few moments ago. IB divided by NLE. So here it's given L is the length. If you will just put the thickness, so you have to use the thickness formula. So IB and LE all is given. So we'll just put the value, and here you can just check here. And if you will just look at the figure, I have taken here the length of the strip will be D, and here I have just mentioned as L is related with the thickness by L equal to A by D. So here basically this L, which is the thickness here. Fine. So the thickness which is given here will be 150 micrometer thick. So here, so check 23 multiply 0.65 divided by the values, you will get 7.4 10 to the power minus 6 volt. This is the second question. Again, the same thing. You have a metal strip, length, width, and thickness is given with the constant velocity, and the B field is also given. Potential difference is given. You have to calculate the speed. Again, the same formula you will use. The formula will be when the equilibrium condition is obtained. You have the speed formula related with E and B. That's in the velocity selector also, E divided by B. And what is E? That is the electric field, which is basically a potential difference divided by D, and D is the distance basically which is shown in the figure, and the B is also given. So the potential difference is given, the B is given, and this width this D is also given here. That is basically 0.850 centimeter. So just substitute it here. Okay, length है आपके पास इस conducting metal strip की. So just substitute the values here. You will able to get 0.382 meters per second. And this is the worksheet, student. That is for your checking of the concept. Is it clear to you or not? If the positive charge carrier will move, and if I will just take the current direction vertically up, then what will be happening? In other words, which side will be at the lower potential, which side will be at the higher potential? You have to explain in it in your answer. So hope so, student, the things are clear to you. Just read the slides, listen the audio recording, and go through the examples which I explained here. And I said do it by yourself by using the copy. So you will do it, and we will discuss the things inshallah tomorrow. Thank you.